Okay, I started recording. Hi, everyone. Last time we introduced computationally secure notion for encryption. So let's dive into it today. Computational security, security of encryption. And what we are doing is chapter 3.1, 3.2, maybe more, but I'm not sure, from KL, CAT 11. Okay. Okay, what was the notion? So we call encryption scheme ED on message space M, key space K, ciphertext C, computationally secure if for all efficient algorithms A, and last time we called this algorithm adversary, maybe this was clear, but maybe not. We call all when we consider an attack against the crypto system, it has to be an algorithm. It whatever procedure attacker has to destroy a crypto system has to be coded as an algorithm. For all efficient algorithms, and efficient here, recall from last time, polynomial time. For all efficient algorithms A, for all messages M0, M1 in the message space. So I took two messages that I take any two messages that Alice could possibly encrypt. They are any values in the message space. So prescribed space where this encryption is designed for, right? Perhaps bit strings of some fixed length. Perhaps bit strings of arbitrary length. That would be the best. For all efficient algorithms, for all
Professor.
messages hello? Yeah.
Hey, Professor, I think you kind of froze on all of us. Do you mind repeating the last few seconds?
Okay, the recording was not going.
It seems like your connection just got a little choppy.
Okay, hold on. Okay, so all I was saying is that the quantifiers go for all efficient algorithms, A, and for all pairs of messages M0 and M1, just like in the case of perfect security definition, the following must happen. If we compare the probability that an attack algorithm, given the encryption under a random key of M0, where the probability goes over a random choice of the key from the key space, and also randomness of encryption and randomness of an attacker, but I will not write that formally to save on time. If I look at the probability this attack answers just bit 1, and I was arguing last time that this is without loss of generality. An attacker, you can think of this bit as a judgment whether the ciphertext, which is input to an attacker, is a message M0 and M1, where the interpretation of 1, a natural one, would be that he thinks it's M1. If he thought it's M0, he would output 0. And sort of answering anything else makes no sense. You know, he can output 2 or 3, but it's not very clear how to interpret that. So let's just say that he outputs a single bit, and this bit is an indication whether he thinks that he has in his hand an encryption of M0 or an encryption of M1. And already here it's for full formality, M0 and M1 are also inputs to A. Okay, so in some sense, I don't have to say this because if the quantifiers go over all algorithms and all message pairs, then notice that this algorithm could in particular have both of these messages encoded inside because the quantifier goes for all. So in particular, those A's that just have M0 and M1 already part of it. But to make it more obvious, we can just add M0 and M1 as another input to A. So I compared this probability with this one, that attacker, given a random encryption of M0, outputs the same bit 1, where this probability also goes over the key space. And I say that this difference has to be less than a negligible function a negligible function.
Should the second one be M1, Professor?
Oh, whoops. Yes, I'm sorry. Yes. Thank you. And now you can ask, okay, this is a negligible function, so it's a function of what? Well, let's call it n, the input, and let n be the security parameter. Okay, now where is the security parameter here? Assume k is like, you know, for simplicity, assume k has n bits. Okay, and also assume that M, the message space, is some subspace of 0, 1, so bits, to some polynomial of n. So in other words, the bit strings that you encode are at most polynomial length in the key. So there is basically, the crypto system says the following. You will have the key of length maybe 100, maybe 200, maybe 300. And there is some, let's say, fixed polynomial. How much bits, how long bit string I can encrypt with this key? This polynomial can be huge, like 1 million times the length of the key. Perhaps 1 million times the length of the key square. Okay, so these might be very large messages, but nevertheless they are limited by some polynomial in the length of the key. And now, okay, encryption scheme also has to be efficient algorithms. So this encryption and decryption are both polynomial time algorithms. So note, key has n bits, the message has some polynomial in n, so the total length of these inputs is polynomial in n. Now, if AE is an efficient polynomial time algorithm, so the input is some polynomial in n, the output must be polynomial in n, right? Because the output is a polynomial of the input size, and the input is a polynomial in n. So if you know this outer polynomial is called p prime and the inner is p, then p prime of p of n is a polynomial in n. So input of A are of length polynomial in n. So the fact that A itself is a polynomial time, it's essentially the same as to say that A is polynomial in n. Okay, so he is, for example, not allowed to have stage brute force attack against this key, because searching through this full of the space, right? If I wanted to do some operation per every key in here, that would take me 2 to the n time, and that's not allowed, right? Because 2 to the n is not any polynomial in n, in the length of these outputs, right? Okay, so this was what we gave last time. Now let me say that this is it's good to cast this in a general language of distinguishing between random variables. So let me define indistinguishability of random variables. Or otherwise known as distributions. Because a random variable is identical to the probability distribution. So we say that D0 and D1, two random variables, are indistinguishable and actually computationally, because there is also a statistical information theoretic notion of indistinguishability. If for all efficient algorithms A, for any efficient algorithm A, probability that A says 1 when he is given a random an input randomly sampled from distribution D0. And if we compare it to the probability that A says 1 when he is given X randomly sampled from distribution D1, we compare the two, and we say that D0 and D1 are negligible if for all such algorithms this distance is at most negligible in n. Now, what is n? Say that D0 and D1 have to range over n-bit strings. Okay, so these are random variables that have at most n bits. There are some n-bit strings. So the input here, X, always has at most n bits. Let's say they always have n bits. So an efficient attacker, well, has to be polynomial in n. This is a generalization of what is happening here, because now we can rephrase this as encryption E, encryption ED, I won't copy the stuff, is computationally secure. If for all messages for all 2 messages in the message space, random encryption of M0, and this is a random variable determined by the choice of the key. So for a random, let's fix the message, it's M0, pick at random a key, and look at the encryptions of M0 under this key. In other words, what is this? This is a random variable equal to random encryption of M0. That this random variable is, I'm sorry, just one more word here. We say that these 2 distributions are indistinguishable, and sorry, I should have said this in a larger font. And okay, unfortunately, I have to write it separately, that we denote the fact that D0 and D1 are indistinguishable in this following fast way. D0 is approximately like D1. And to say that this approximation is computational, we have this funny symbol. They are like as far as computation goes. Okay, as far as the polynomial time computation goes.
Professor?
Uh-huh.
I was wondering, what is D0 and D1 in the indistinguishability of random
Any two random variables. Yeah. So I will just give you an example here. I was about to exemplify usage of this notation.
Okay.
So D0 and D1, let's actually think of them as what's D0? It's a random encryption of some message M0. What's D1?
Okay.
For example,
random.
Yes, so this will be my first example. Encryption is computationally secure if for any two messages in the message space, the random encryption of the first message is computationally indistinguishable from a random encryption of the second message. And where the key is random from the key space. So here, this is your D0, and this is our D1. Hold on, I don't think it's super in focus. Okay. Okay, did I freeze again? I see that the chat says that I was frozen, but do you think that you lost some stuff because I was frozen?
It wasn't for very long the second time.
Okay.
I think it was okay. Sorry,
I wasn't monitoring the chat. Okay, so sorry about that. Okay, so you see this definition is exactly the case of this applied to the following two random variables. The first distribution is random encryption of M0. The second is random encryptions of M1. And we can restate this as follows. Encryption is secure if for any two messages, random encryption of the first message is computationally indistinguishable from a random encryption of the second message. What's the intuitive meaning of computational indistinguishability? The meaning is this. Maybe it's better to consider this pictorially. So you have some attacker, and he's get an input X, and he has to output a bit, which is 0 or 1. And there is two cases. X is taken as random from the distribution D0. For example, D0 is encryptions of some message, let's say, I love you. Case 2, X is taken from distribution D1. For example, D1 are encryptions, and now encryptions, what does it mean? Why do I use plural for random key? So that's why there's many encryptions, right? I pick a random key and I encrypt this fixed message. And D1 are random encryptions. So maybe I should cut the plural, right? Because it is a single encryption, but it's a random variable, right?
Does that
And
mean does that mean D0 is the set of all encryptions of I love you
it is not
on
a set.
all possible keys or
It
distribution?
is not a set because, for example, for some keys, perhaps they collide and they make, on some key, perhaps an encryption of M0, there is two keys. If you encrypt M0 under those two keys, you get the same ciphertext. So it's not a set because that ciphertext has a higher probability than some ciphertext that there is only one key that encrypts M0 to that ciphertext, right? So if encryption is in some sense efficient, so it uses keys efficiently in the following sense: for every message, the encryption function is one-to-one, so it does not have a collisions with respect to keys. In other words, encryption of M under K1 can, if this equals, then K1 is K2. So let's call E is key efficient.
And that would be a uniform distribution.
So
in that case,
if E is key efficient in this way, then I can, basically I can think of these distributions as simply sets of all possible ciphertext of M0 and uniform distribution over that cipher of the set. Right? So you are right that in this most common case, you can think of, it just simplifies to simply a uniform distribution over the set of possible encryptions of M0.
that makes sense. Thank you.
But unfortunately, this is not guaranteed for many encryptions we'll see. So that's why we don't want to make these limitations. It's not guaranteed, and actually it's not going to be even the first encryption scheme we'll see that does not have this property. It's not guaranteed to have this property. Okay, so M1 is okay, sorry about that, but like I hate you, yeah. And he gets, in this second case, he also gets an encryption, this variable X. So maybe I shouldn't say that he gets, because it looks like he gets two X's. No, he gets one, and he's an algorithm. His input is only X. That's the only thing from which it wants to conclude. Is he in case one? Did he get X from this distribution, like a random encryption of I love you? Or did he get X from this distribution, like random encryption of I hate you? And he wants to decide, and without loss of generality, it's just a bit decision where we can interpret one as thinking, I think I'm here, and 0 as I think I'm here, right? And sorry about these indexes, because it's just when we think of bits, it's convenient to index everything by a bit. So to consider D0, D1, but when we speak, it's kind of bad to case 0 and case 1, right? Like it's more, I have first message and a second message, and not zeros message and a first message. So there's unfortunately going to be this, I would say first message, second message, but unfortunately this one is designated M0 and this one is M1. Okay, but it is just, you can call this M1 and M2. Right? It's just that then you have called this bit 1 or 2 and is no longer a bit. Okay. If these two distributions are indistinguishable, then every efficient attacker A outputs, let's say 1, given X from this distribution, with roughly the same probability as he outputs 1 on X from this distribution. And what do I mean by roughly? When I compare them, they are a negligible function of the security parameter, of length of these strings. So if I just hike up this security parameter to the level I deem secure, this is, a fast vanishing function. So it can attain any level I feel safe with, like 2 to the minus 100, sure. And there will be some realistic n that will make this less than 2 to the minus 100. If I want 2 to the minus 200, I can do that too, just hike up n sufficiently enough. So therefore, from the point of view of any efficient algorithm, these two distributions are indistinguishable. This means that whatever this algorithm does, his outputs are effectively the same. Where effectively, I mean upper bounded by this fast vanishing function. Okay. Here is another pictorial way to show what this computational what computational security is, and I think that this is an attractive way to show it, to portray it, because it looks like a game. Sorry, I'm kind of a problem adjusting these things so that to try to show them on one piece of paper. Okay. Computational and computational security of encryption is otherwise known as computationally indistinguishable. So unfortunately, we use the same word, indistinguishable, to designate the property of any pair of random variables. And we use the same word, indistinguishable, as a specific property of encryption, where we call encryption indistinguishable if for all two messages in the message space, random encryption of one is computationally indistinguishable from a random encryption of the other. And I cannot do much about it. This is a terminology that always confuses people, but unfortunately, that's an overload of this word. It's both used for any two random variables and specifically for an encryption scheme where the meaning is this. And there is yet another way to name for this definition. It's called semantically secure. Maybe I will say why it is called semantically secure a few slides, somewhat later. Okay, so it's clear why this notion is called indistinguishability. Why it's called semantic security, I will explain later. Okay, so computational same definition, different form. we say that encryption scheme ED and K, M, and C, which are the key space, message space, and ciphertext space, it's part of the specification of an encryption, is indistinguishable. If for all efficient algorithms A, the following is true. The following probability that B prime is B in the following game is negligible. And now let me describe this game. So first, bit B is chosen at random, like so. Then a key is chosen at random in the key space. And then an attacker actually has to specify what are the two messages that they must be in the message space that he wants to encrypt. And okay, and we will enforce that these two messages are of equal length. And this in particular is implied if the message is bit strings with some from some space like this, where P is some polynomial. So you see, bits of fixed length, whatever length that is polynomial in N, every element of M has the same length, namely P of N. So in particular, if I choose two messages in the message space, well, they both have to have that length. So this follows. Okay, so an attacker chooses two messages in the message space, and what he gets back is the ciphertext, which is a random encryption under the randomly chosen key of MB, meaning whether he sees an encryption of M0 and M1 is decided by this randomly chosen bit. Then he outputs a bit B prime, which is his judgment as, you know, does A think that he gets that C is an encryption of M0, or does he think that C is an encryption of M1? And okay, I'm sorry, I just noticed that I made a mistake here. This probability cannot be a negligible function. It without loss of it can easily be 1/2, but we ask that it's no more than 1/2 than a negligible function. So this is the game. Okay. It's to me, it's it looks attractive because think of an encryption as an experiment involving an attacker. Attacker specifies any two messages in the message space, the worst messages that he wants some application to encrypt. Perhaps M0 is like some particular PDF that is set of custom rigged so that its encryptions are somehow different. You know, these encryptions can be distinguished. M1 is another PDF, again rigged in such a way so that somehow its encryptions can now be distinguished. And this poor person chooses a key at random, as they're supposed to, and follows encryption E algorithm on this random key, and unfortunately he encrypted, in one case M0, perhaps in the case, when perhaps whether he encrypts this type of PDF or that type of PDF is somehow related to, what kind of person he is, right? And that's what attacker wants to distinguish. Is it this kind of guy or this kind of guy? And no matter how attacker rigs these plain texts, every efficient algorithm that chooses these two messages and then gets a random encryption of either of those, if he tries to guess which one it was, so what is the essential bit that he wants to guess? Is this bit. This is the bit that said, I'm the kind of person who encrypts M0, or if B is 1, I'm the kind of person who encrypts M1. And we're measuring the probability that an attacker finds out what kind of person.
Hey, Professor, you're frozen again.
Oh, okay. So, yeah. This network, usually works, but it somehow refuses to work today. So, what do you think was the last part you guys heard? A is just responding to a chat. A is adversary algorithm. Yeah. A is, we call this algorithm A because it's like attacker, adversary. So that's why we customarily call an attack algorithm A. So the attacker is trying to, okay. Note that this probability, just 1/2, is trivial. If B is a random bit, then attacker algorithm can ignore the ciphertext and just outputs B prime in any way he wants. B prime can be a random bit, and still these two bits would be equal with probability 1/2. This B prime can be a fixed bit. So A can just always output 1. And note that here, so hits this probability, this equality is assured with probability 1/2. Sorry, now I have some choppers outside of my window. Right? Or this bit can be just fixed to be 0. And again, this bit is equal to that one with probability 1/2. So 1/2 is trivial. Anything more is, well, possible, but it has to be a negligibly vanishing function. It is kind of an exercise why so if we call this definition 2 and we call this definition 1, then definition 1 and definition 2 are equivalent. Exercise. Okay, so this is explained in the book at some point. Also, Ye can go over it, but it's not hard to see that the notions that says that any attacker, when he wants to output a bit, if the probability that he outputs some fixed value 1 when he gets an encryption of M0 is indistinguishable from outputting the same bit when this input is an encryption of M1, then in this game, these two bits can be correlated at most with this probability. So that's the argument that if you define encryption security in terms of definition 1, the definition in this form follows. But the opposite is also true. Okay.
So in that example, Professor, in the box that you just did, is that kind of like a trivial case, since it, like you said, the attacker could just ignore the ciphertext altogether and just randomly.
This is trivial. If you remove the negligible part, if you just say that hold on a second, let me think, what am I saying? No. What I'm saying is that it's easy to show an attacker that achieves this, that this probability is equal to 1/2. This probability can very easily equal to 1/2. Because, for example, consider the following very simple algorithm A. He ignores the ciphertext and just output B prime with B prime is a random bit. Then these two are equal with probability 1/2. Some other quote unquote strategies work just as well. A can ignore the ciphertext and just output a fixed bit. It's always 1. And still the probability that this random bit is equal to that one is 1/2, right? So it's very easy to design an attacker who achieves the bound 1/2. What this notion says is that, okay, these are trivial attackers. They get bound 1/2. But what this says is that every, including non-trivial, however complicated, but still efficient, meaning polynomial time, he might get this B prime slightly correlated with B, but only by this amount. So he can go over the trivial bound of just guessing B only with this negligible, by this negligible amount.
Okay, that makes sense.
Okay.
Thank you.
Okay, great. Okay, let's look a little bit what the consequences of this definition are. Okay, I mean, to see that these two notions are very similar, look, bit B determines whether attacker fixes these two messages, possible messages M0 and M1. If this bit is 0, then this ciphertext is generated from this distribution, where D0 is random encryption of this M0 that attacker specified. If this bit is 1, then this ciphertext is a random variable like this, is chosen from the distribution of random encryptions of the M1 message. The first definition said, I call encryption secure if any attacker, if every polynomial efficient attacker cannot distinguish between these distributions. In other words, the outputs that an attacker outputs are the probability that they attain whatever fixed value is effectively the same, whether his input is from D0 or his input is from D1. This implies this game, right? This notion. Okay, I think I'm running in circles here. But okay, I think that visually it should be clear that when he gets here is the same, is either a random encryption from M0 or a random encryption from M1, and his task is to judge which case it is, which was exactly the notion we considered here, right? He gets random encryption of M0 or random encryption of M1, and he wants to judge between these two, and his success rate is bounded by a negligible function. Okay. So let's do some exercise. Is one-time path computationally indistinguishable encryption? Well, one-time pad is perfectly secret. It's perfectly secure. And this notion of indistinguishable encryption was supposed to be a relaxation of this one. So perfectly secure encryption should be a subset of the computationally secure ones. Okay, let's see if this is true. Okay, so let's see if this notion is true. So let's say, okay, attacker picks two messages, and it's a one-time path, so these messages must be n-bit strings. Okay, the length is n. Now we choose randomly one of them, and we choose key in a key space, but it's a one-time encryption, so it's an n-bit string. And we send a ciphertext, but we use a one-time path. The encryption is a one-time path. So C, an encryption of K on of MB, is what? It's just key K XORed MB, right? Because this is the it's a one-time path encryption. So and now A outputs some bit B prime. But by one-time path security argument, the random variable formed like this for every B. So that doesn't matter whether I'm encrypting M0 or I'm encrypting M1, this random variable, right? So I take a random key and I XOR it with MB. Well, this random variable is identical to the following one. I take C at random in the space of n-bit messages, right? That was the argument, which I'm not going to repeat, why one-time path was secure. So this is the C. And for both M0 and M1, this variable looks like that. So in both cases, B0 and B1, this input of A looks like this. It's just a randomly chosen n-bit string. So this information basically is not preserved in the ciphertext. The ciphertext is independent of bit B. So this follows that C is independent from B. And therefore, B prime, of course, if the input of A is independent of something, then clearly the output of A must be independent as well, right? Because, if the input contain no information, then how come, then how possibly outputs, right? A is an efficient algorithm. All it can do is to process the inputs in some way. If the inputs don't contain this information, then neither do outputs. So the B prime must be independent from B as well. So therefore, probability that B and B prime are equal are exactly 1/2. Okay, so one-time pad is an example of a cipher where this trivial bound of 1/2 probability that B prime and B are equal is in fact the best possible. You don't have to take a stupid algorithm to make this. Every algorithm can, can only achieve B prime be equal to B with probability 1/2. So the fact, so yes, it is right, because for the probability, this is a case of that for the negligible function equals 0, which of course is negligible, right? So 0 is like the best negligible function there is. It's it's as small as you can for every n. This notion is a relaxation of what happens. So if we replace, there is two places where this definition relaxes one-time perfect secrecy. It's this and it's this. If instead of efficient algorithms you said any, and instead of requiring that this bound is at most negligibly larger than 1/2, but instead saying it has to be 1/2, this would be perfect security of encryption. And the relaxations are in these two places. Okay, so one-time pad is indistinguishable. Let's see some encryption which is not questions about this. Sorry, it's such a okay. Just when I position it correctly. Did I lose somebody here? Okay.
Professor, I had a question about the.
Yes.
Yeah. I didn't understand the argument that for every B, K, XOR, MB, that part.
Well,
what is the
well, it is an argument that we said we gave two different versions of this argument in the first week of the class, when we argued why one-time pad is perfectly secure. Perfect security of one-time pad follows from this statement, that no matter what you encrypt, if you encrypt that a message by XORing with a random bit string, it is perfectly secure encryption, because such process start with any message and then XOR it with a random bit string always results in just a random bit string independently of what message you started with. And therefore, the result of such an XOR hides this input perfectly. And therefore, whether this is B is equal to 0 or B is equal to 1, in both cases, this value is a random bit string. So that's what I mean is that C is independent from B, and therefore the output of A is also independent from B, and therefore this is the case.
I see. Yeah, makes sense. Okay. Thank you.
Okay, great. So here is, let's call it question 1. And let's call it question 2. Is encryption which leaks, let's say, first bit of plain text, indistinguishable. So what does it mean that the encryption leaks the first bit of plain text? I.e., there is some efficient algorithm, let's call it A, such that A, given an encryption of M, simply outputs the first bit of M. And this holds, for simplicity, for every key in the key space and every message in the message space. So M1 is the first bit of M. Okay, and yeah. And okay, so assume this is bit strings. Right, so your messages are bit strings. So yes, there is an efficient attacker, efficient algorithm that if you give him as input an encryption of M under key K, and no matter what M is and no matter what key is, this attacker can, given that ciphertext, predict the first bit of the message. No other bits, but the first bit, yes. Okay. So the answer is, well, okay, maybe it's facetious of me to ask. Well, but let me ask you, so you, okay, no, it's not really, because you can, I don't expect you to be able to work with these notions quite yet, but I'm going to say is no. Okay, and so let's recall this notion again, right? So how can I say that it's not an efficient encryption? Well, I have to just show an attacker that will beat this bound. So the probability that B prime is B is going to be not upper bounded by 1/2 plus negligible. Actually, so why? There exists efficient algorithm A prime, which violates the encryption indistinguishability gain notion, and it violates it very badly. The probability that B prime is B is going to be actually equal to 1. So he will predict this bit perfectly. This bit B prime is just always going to be equal to B. Okay, let's see how that attacker can be done. Okay, here is the code of the attacker A prime. Attacker A prime will use this attacker. What does he do, attacker A prime? So, well, first of all, how does he choose these two messages, M0 and M1? So here is an algorithm. Pick M0 and M1 in the message space M, such that, oh, okay, damn, I have an issue. It's a notational issue. So, you know what? Let me change this. I'm not going to call it M1. Let me call it LSB of M. So this stands for least LSB, least significant bit of M is the same as first bit of M. Okay, it's the least significant bit of this message. Why I don't want to use indexes to signify bits? Because I use indexes to signify two different messages right here. So now I have a notational issue. How do I designate the first bit of M0 and the first bit of M1? Okay, so pick M0 and M1 in such a way that the least significant bit of M0 is 0, and the least significant bit of M1 is 1. So in other words, M0 and M1 are any bit strings which differ on the first bit, and let's call the message with the first bit equals 0, M0, and let's call the message with the first bit equal 1, M1. And these would be the two messages this attacker says, I will break this notion by using these two messages. Okay, so now let's see what happens. Bit B is chosen at random, and the key is chosen at random. And what this guy gets is a random encryption of MB. Well, he feeds this encryption, this ciphertext C that he received to an algorithm A. And this algorithm is going to tell him a bit. Let's call it this bit B prime. And A will just output, okay, you know what? So let me not show it like this. Given C, output whatever A B prime, which is equal to the output of A on the ciphertext C. Now, what was the assumption on A is that no matter what key is used and no matter what message, the A given a ciphertext always outputs the least significant bit of the message. So probability that B prime is B is the probability that A on random encryption of MB outputs B. But that probability is 1 by this fact and this fact. Because, okay, by fact A, okay, let me just write it like this. This is the probability. Now, what do you know of A of E of K of MB? This is always equal to LSMB of MB. And this is by fact 1. So by fact 1, A given an encryption for whatever key of M always outputs LSMB. So this string, output of A on encryption of MB, is equal to this string by the property 1. And this is 1, and this is 1 by property 2. Right? Because M0 and M1 are created in such a way that this statement is always true. No matter whether if B is 0, the statement is true. It's right here. If B is 1, the statement is true by this. So cutting to the chase. And A was an attacker that predicted the first bit of the encrypted message. If the two messages differ by the first bit, then that type of attacker that predicts the first bit of the message encrypted in C is going to break the indistinguishability notion of encryption. Because precisely given an encryption of M0, he will always output 0. And given an encryption of M1, he will always output 1. So he will correlate this bit with that bit perfectly. Therefore,
wait, Professor, could you repeat that last part you said?
Well, I believe that was that that this type of attacker who predicts who can tell the first bit of an encrypted message will break this notion would break this notion by making B prime and B always equal. So in other words, he always predicts this bit B perfectly. He doesn't guess it at random. He just knows what it is. Okay.
Oh. Yeah. Okay. Yeah.
Okay. So if an encryption leaks the first bit, then it cannot be indistinguishable, i.e., therefore, if E is indistinguishable, is an indistinguishable encryption, then E cannot leak the first bit of a message. Okay, because we just did an exercise that if it does leak, then there is a trivial attack that uses this fact that it leaks to attack this notion. Was it important in this attack that it was the first bit? No, not really. If this was the 7th bit, then the attack would differ only in that I just pick M0 and M1, who instead of differing on the first bit, they differ on the 7th bit. And then what I get here is an encryption. And I feed it to this guy who supposedly, given a ciphertext, predicts the 7th bit of the message. And again, I use this bit to know, okay, if that 7th bit was 0, then I'm in this case. And if that 7th bit was 1, I'm in this case. So, actually, easy generalization is that an indistinguishable encryption cannot leak any bit of plain text. Okay. Even these bits that cannot be leaked don't have to be any particular bit of the plain text understood as a bit string. They can be a bit as in information. So imagine that the message space is divided by two partitioned. That there is some function I, I'm going to call it information, that given assigns a bit to every message in the message space. So these are all M such that this information on M says 0. And these are all M in the message space such that the information is 1. Examples. I of M says 1 if M is a PDF, okay, and 0 otherwise. So this information is like, is this message a PDF? Or, you can put anything else. Yeah, I of M is 1 if M is an English sentence. And 0 otherwise, right? Anything you want, like M is HTML or XML with some particular format, whatever, right? M is IP message whose port number matches something. Okay, and Yeah, so any information function on the message space. And if E is an indistinguishable encryption, then E cannot leak I of M, i.e. For all efficient attackers A, it must be the case that the probability that A, given a ciphertext, which is an encryption of K of M for random key, that it predicts what this information function on the plaintext is, it must be at most, well, now, at most what? Because let's see, what is the distribution of M? Well, let's say I'm taking them at random from the message space. Now, of course, these two sets might have different sizes. So the subset of all messages that encode a valid PDF, this one, might be tiny. So this is the case where I of M is 1 is very small subset of the whole message space. So hold on a second. I don't want to bank on this definition. I'm already thinking that what should it be? The effect should be that the ciphertext is useless in predicting this function, the value of this function, but the value of the function, if I'm say I take a random M, well, there is if values that have, if I of M of a random message has, is 0 with much larger probability than it's 1, then there is an attacker here. He will just always output 0, and he will be correct with a lot of cases, right? Okay, you know what? Let me first remove this and just pretend, first consider the case that that both subsets have size half of the message space. Okay. Then basically if he's given a random message, well, he can predict this bit with 1/2 probability, and this is at most what he can do. Okay. So sorry. Here I considered a sort of a stronger type of attacker, which given a ciphertext, predicted this bit function perfectly. So for every key, for every message, it just outputs this bit function of the message always. Here I'm relaxing this. I'm saying Well, perhaps he doesn't predict this bit always. He just predicts it with the probability 1/2 plus negligible. Okay. And the point is that if encryption is indistinguishable, then his ability to predict this bit function is upper bounded by a trivial amount, plus it can only be negligibly higher than a trivial. Why is this trivial? Because again, it's random guess satisfies this with probability 1/2 if the two subsets have equal size. There is a way to generalize it to to these interesting cases. Okay. Basically, the generalization is like this. They don't have to have equal sizes. I can consider any small subset of the message space, and I can consider a baseline probability that if somebody takes a random message, what's the probability that is in this subset? So in other words, what's the probability like of a trivial algorithm of predicting this function on a random message? Let's say that this subspace has 1/1000th of the large one. Well, then with probability 1 in a I can predict with the probability actually 999 over 1,000 without even seeing the message. I just always say 0. And I'm correct with 999 in 1,000 cases. And encryption is if encryption is indistinguishable, then given a ciphertext, I can predict this function with the base probability plus negligible. Okay, so if there is some base probability of telling, okay, a random source is a PDF or a random source is not, then there's some base probability of predicting whether an encrypted message is whether a message chosen from message space is a PDF. The full version of this notion would say that any efficient attacker, if he gets a ciphertext, he can predict this key target information about it with probability that's the baseline one, only negligible away from the baseline one, okay, from the baseline prediction of this information function on a random message. And that is, by the way, why this encryption is called, this notion of encryption is called semantic security, because it says that an attacker which given an encrypted cannot tell any information about this message with probability better than significantly better, so only negligibly better than a trivial prediction of this information. Trivial meaning, well, I know this full set from which the message is chosen, and I know that half of them have this information and half of them don't. So with probability 1/2, without even seeing ciphertext, I can tell what that message is, what that information is, right? Just I'm cast a bit at random and I'm correct with the probability 1/2. So that's a triviality. The question is the ciphertext allows anyone to beat this triviality condition? And encryption is secure if every efficient attacker can beat it, but only by this negligible amount. Okay, so in other words, if you are interested whether the encrypted message is a PDF, well, you can't. You can't tell it in any better way than a priori a probability that a message taken from, that you think that, Alice is, let's say, that Alice is encoding HTML documents, but with some probability they are of the type you're interested in. is the ciphertext allow you to predict whether she is encrypting the ones that you're interested in any better way than from what you previously knew about this distribution? And this, what is implied by the indistinguishability of encryption is that no, you cannot. If you could, then the same algorithm, then the same style of attack would work, because you would choose these two messages. One of them is with this has this, it falls into this pre-image, the other into that pre-image, and the attacker who can predict which of these two the encrypted message is breaks this notion. It's just a generalization of this attack. Okay. I have gone a little bit over time, trying to argue these implications. They are also written in a pictorial form on my slides, and I will edit the website to tell you exactly, how much of Catherine Lindell we have just gone over. Maybe I will stop recording. If you have any questions, you can ask after.